Hey, happy Valentine's. My name is Carrick Johnson. This is FTT122 and assignment number 6. So the first thing that we're going to talk about is trajectory and sights. So using everyday objects. So this is kind of a rudimentary example of trajectory and sights, this being the center of your bore, this maybe being your optic. So depending on how you want your zero, maybe you want a little further out of a zero where your optic is going to be intersecting this imaginary point coming out. This may be more of a point blank. We as shooters know that a rifle doesn't actually, the bullet doesn't actually rise, but instead maybe we have to, because of our sights, we have to angle it upwards to get to where our line of sight is looking through there. Next I'm going to talk about is gyroscopic drift. I'm going to be using an arrow. So a lot of fletchings, how you get spin on an arrow is by the shape of your fletchings. So by putting a rightward spin, and with this broadhead being tuned properly, depending on its spin and its interaction with gravity, with this spinning rightwards and gravity is force down, this arrow is going to drift to the right from its target eventually. Drag is just pressure on the nose of a projectile, which I just had a projectile here. This is my everyday object, so I like it because it's got a red tip and you can see that's where it's going to get the most drag. So it is parallel pressure to the center of the spin, and any force outside of that is going to generate lift. The Magnus effect, I think, is going to be kind of hard to demonstrate, but I've got a muzzleloader jammer, but just pretend like the stick's not here, and this is say a baseball. So because of so we throw this baseball and it spins like a curveball. Based on where we're adding spin to the object is directly related to how that object is going to react with its force. So we're going to throw this baseball and put a rightward spin on it. As this baseball is spinning through the air, it's going to kind of come in an arc and come back around. And that's because there's lower pressure on the bottom and higher pressure on the top. The Coriolis and Eötvös effect. So using the same object here, if this is a globe, right? Let's say this little doohickey here is the equator separating the northern and southern hemisphere. So with the Coriolis effect, it doesn't matter if we're shooting north to south or south to north. Based on the Earth's spin, we are always going to impact to the right. And that's all due to the Earth spin. So the Eötvös effect is when we are shooting east to west, and when we are shooting west, the target will rise by 2 inches and we will end up shooting low. So, and that's per 1 second of flight time. Opposite is true if we're shooting east, we're going to end up shooting 2 inches high. Vertical angles. So I don't really have anything better to show as an everyday object except this dope card that came with my rangefinder, and you have to know the slope and your existing drop of your firearm. It's got a slope angle of 14, 22, 25, 31, 34, 37, 40, 43, and 45. So it does stop at 45 degrees. I don't know why it stops at 45 degrees, but that's just what the card shows. But in hunting applications, I basically, if it's a slight grade, I'm going to say 14. I know what a 45 degree slope looks like. You know, that's pretty easy. And if it's somewhere in the middle, I'm just going to choose a 31 degree. But then you got to know your existing drop data, and not in inches, in MOA or milliradians, depending on how your scope is. So I'm reading from the MOA side, but most of my scopes are in milliradians. But let's say if I have I'll just flip it around. Let's say if I got a 4.1 milliradian drop, and I am shooting at, and that's with level ground, and then I'm shooting at a 45-degree angle, that is I'm going to only adjust 2.9 milliradians. If it's a slight grade, with my flat trajectory at 4.1 milliradians, I'm only going to go 4.0 milliradians. And that's basically, it's always going to impact high. So transonic ballistics, I'm going to use my turkey striker here. So as a bullet, so as a bullet's flying through the air, in front of it is the sonic boom, and this bullet's pretty stabilized, it's flying through the air, but when it slows to being subsonic at about 1100 feet per second, we are going to it's going to start to destabilize because of the turbulent air created by the shock wave. But a properly stabilized projectile will come out of it and get back to it. And a projectile that is improperly stabilized will continue to destabilize through its target, to its final destination. One thing I would like to research on my own is projectiles that are subsonic and stay subsonic, so there never is a sonic boom. So being it properly stabilized, there's no transonic zone. So that's my presentation. Hope I covered everything. Thanks so much. Have a good day.